Practical Fish Keeping, July 2021. The brightest pupils. Ever noticed how some catfish have eyes that are starkly contrasted to their bodies? Steve Grant explores the reasons and mechanisms for this seemingly evolutionary mishap. For most of the darker coloured plex, the main iris colour, the area around the pupil, is brown or black, and this is so the eye colour blends in with the fish's base colour. Some species have white or pale, yellowish or golden, or just plain greenish eyes, and for the same reason, to blend in with their overall colour in order to camouflage the eye, which would otherwise be conspicuous. Occasionally, there are species with reddish or blue eyes, and unusually, these are not the same as the head colour. For example, Panax cochylodon have obvious blue eyes in contrast to their bodies. As aquarists, we look at these colourful-eyed species and find them attractive, but have you ever wondered why their eyes are so unusually coloured? Well, there are reasons. Fish eyes. Let's firstly look at why catfish eyes are the way they are. Unlike humans, the pupils of most teleost fishes cannot change in size in response to levels of illumination. This is not the case for most loricarid, sucker-mouthed catfish species, which has a flap on the iris that can extend downwards over to cover some of the pupil. The covered pupil in the loricarids has the shape of a crescent or an upside-down Greek letter, omega, and for this reason they are sometimes referred to as omega eyes. Some shallow water fishes from several groups of teleosts are able to change the corneal coloration according to the illumination level. Quite colourless in the dark, their corneas may become yellow, white, orange, or even deep red under direct sunlight. The partially white eyes of some chakra species may be an example of this. Omega eyes. A study in 2002 suggested that the flap in the iris distorts the shape of the eye and blends in with the rest of the fish's body markings when viewed from potential predators from above. They state that the catfish would, however, be able to maintain vision through its crescent-shaped pupil in the anterior, front, posterior, rear, and ventral side directions. While this theory for a reason for the iridial flap sounds plausible, in the extreme case of Panax cochylodon, how does a larger area of bright blue, when the flap is closed on a black body, help to camouflage the eye more than if the flap was open, resulting in a larger black eye with a smaller blue iris? While it would not make the overall eye less conspicuous in this example, because there would still be more blue pigment on show, it would conceal the pupil more, and it turns out that it's a round pupil shape and dull black colour that is visually recognised and used by predators to locate prey. In addition, although the blue or red eyes have an iridescent sheen, the cells that create this can be altered by the fish, depending on the angle of the observer. The colours look hazy or blend into the surrounding colours of the water. Mr. Blue's eye. It's worth briefly reminding ourselves what colours are. Perception of colour derives from the stimulation of the photoreceptor cells in the eye of the observer by electromagnetic radiation or light. Colours of objects appear to the observer through wavelengths of the light that are reflected from the object. This reflection is governed by the object's physical properties such as light absorption and emission, in this case iridophores and melanophores. Not all animals perceive the same wavelengths or spectrum of light, and therefore not all animals see the same colours. Most fish species are thought to have colour vision. Some fish can see ultraviolet, and some are sensitive to polarised light. As light passes through the greater depth of the water, colours, the different wavelengths of light, are selectively absorbed by the water. Water preferentially first absorbs red light, and to a lesser extent yellow, then green, then violet light, then blue, so the colour that is normally least absorbed by water is blue light. However, colour absorption is also affected by the turbidity of the water, the speed and bend of movement at the surface, and the colour wavelengths that can be dissolved by various dissolved minerals, including salinity and organic matter. This is why, to certain depths and salinity, most clear water looks green and deeper still blue, but some river water appears to be brown due to dissolved organic matter. The bright blue or reddish eyes that we see in an aquarium would not look the same in a natural biotope water and illumination. In an aquarium, the water is much clearer, well filtered, usually shallower, and receives different angles of light, even more so from inside illuminating camera flashes, rather than one main source of downwelling light in a river. We are also used to seeing their eyes from the side, whereas some predators would not. Humans may also perceive different colours to the fish's predators or conspecifics. All these factors and others affect how reflective and the colours of the eyes appear. At night, when some of these fish are active, in their natural environment they will appear as and perceive different colours, due to moonlight and starlight reflecting or emitting different wavelengths and intensities of light. So the question remains, why would a vivid eye that doesn't match the colour of the fish's head evolve, especially when most related colours don't have such an eye colour? I've been able to communicate with ichthyologists, explorers and aquarists who have personal experience of seeing some of these species in nature. If we can identify behaviour and the depths, water clarity and composition where these fish are found, they may provide some clues as to why their eyes can appear blue or reddish to us. Panax suttanorum, blue eyes. Dr. Donald Taphorn states that as P. suttanorum comes from the Lake Maracaibo Basin, the waters there all come out of mountains and in current times are quite muddy due to human impacts. Before this, most of the basin would have been heavily forested, which probably meant the water was only muddy during the peak of the rainy season, with clearer waters for most of the year. Donald explored around 400 sites in the area in the 1970s. Most P. suttanorum lived over a rocky substrate with gravel and sand, and plenty of submerged wood. In those places, the pH was almost 7. The waters they live in is estimated to be 2 to 15 metres in depth. Panax nigrulineatus, reddish eyes. Ivan Mikulji filmed this species in the Rio Tiznados, Guacaro, Venezuela, Llanos, and the video can be found at www.youtube.com/watch V=B3CGNT GIFA. An image is featured in Ivan's book, Mikulji 2020, of the specimen on plants, but as can be seen from the video, the fish is first found on the bed of the river, presumably in the deeper part. Where the fish is first found, where the water is clear water, albeit with a bluish tinge, the fish swims off the visibility in the distance, and the distance lessens. At a relatively close distance, the eye is not conspicuous at this part of the river. When the Ivan catches up the fish in shallower water, the water is clear and the visibility is much better. Ivan shines his torch on the fish, and one can observe that as he does this, the brightness and therefore conspicuousness of the eye changes. Without the torch, under natural conditions, the eye colour is not as obvious nor as vivid. Panax ambrusteri, pink to gold eyes. Oliver Lucanus took a fantastic photo of this species in a tributary of the Teles Pires River, Mato Grosso State, Brazil. The first thing that may be obvious to keepers of the species is that from a distance the strikingly bright body stripes that one normally sees in an aquarium are not actually as noticeable in their natural settings. Combined with their dome-shaped bodies, they are well camouflaged even in clear water, although there is some slight turbidity. In the aquarium, the eye of this species is not as reddish as some of the other reddish-eyed species. They appear pinkish or goldish in some settings, but the colour of the eye in the specimen photographed by Oliver is not distinctive. The iridial flap is closed too. Blue eyes crying in the rain. There are some apparent commonalities between the species and others with blue or red eyes. All of them live primarily in clear water environments, albeit with some of the larger specimens of Panax species habituating deeper depths where light and colours visible to humans is reduced or not even visible. Most of them do live amongst rocks and in some cases wood, which provide them some cover from downwelling light, but in most cases still being subject to high levels of relatively unabsorbed or unscattered sunlight. Some of them sit in open water, but when breeding probably breed in enclosed spaces. How big, how blue, how beautiful. The complex structures of chromatophore cells and control mechanisms and the colours that they show to the observer will not have evolved by accident. Conspicuous coloration can be associated with mate choice, species recognition and communication, crypsis and vision improvement. Some bright colours such as red and blue can be aposematic, a warning coloration to predators showing the fish's unpalatability. Many colours are therefore a compromise between being visible to the intended receivers while avoiding the attention of the unintended, by which I mean predators, or in the case of aposematism, actively getting the attention of a predator. These opposing forces drive the evolution of adaptive, context-dependent coloration. The directionality of iridescent colours might allow fishes to direct their signals at intended receivers, such as prospective mates or rivals, but also to avoid unnecessary conflict with members of the same species. It is very likely that the iridescent unusual eye colours have also evolved due to functional reasons. All the species discussed live in clear water with little or no turbidity. All of them at least visit shallower waters where red light spectrum is still abundant. Most of them sometimes sit out in the open or shallow or deeper waters. As adults, most visit deeper waters where blue light is the most abundant and red light least abundant, if present at all, and where non-iridescent colours may be less visible. All of them spawn in enclosed spaces, which would need defending and would require enticement of a member of the opposite sex. My own hypothesis is that the iridescent blue and reddish eyes carry out a variety of functions, which are under physiological control by the fish, dependent on the need at the time it is deployed. Eye camouflage, filtering and enhancement of light for varying lighting environments, all depths they may occupy, and intraspecific signalling. The latter may involve signalling to competitors for hiding and breeding spaces, and potential mates for the breeding. There's much more to this matter than meets the eye.